Here's the last section we skipped. In it we define some functions in terms of integrals. This is one of the least important parts, but I will give you a few homework problems on this. And it just does this. In the early part of the book, the review section, they define the logarithm ln of x, the natural logarithm, as the inverse of e to the x. That's fine, but it's very complicated because it leaves questions like, how do you find e to the x for x, an irrational number, one that can't be written as a fraction? You can't interpret that as a power and a root anymore. And then how do you define ln as the inverse of that? Well, all those problems are avoided and the definition comes more naturally if you instead define the natural logarithm as the integral of 1 over x. And it goes into a little bit of history here. These page numbers might be a little bit different than in your book. Here we go. Here's another way to define the natural logarithm. Instead of deriving from the algebra definition that the logarithm is the integral 1 over t, as was previously done, and then have it only be defined for certain numbers, we'll say instead that the logarithm for x greater than 0 of x is the integral of 1 to x of 1 over t dt. And this defines it for all real numbers x. Immediately, you don't have to go back and worry about those special cases. If this is the definition, then one thing you know from the fundamental theorem of calculus, when you have an integral going from a fixed point to a variable point x of a continuous function, like 1 over t, the derivative of this function is just this function on the inside with t replaced by x, right? Simply because the derivative of the integral gives you back the function inside. It's just you have to put x instead of t. So we'll say that the result, that's a simple theorem, I just stated the proof. The derivative of ln x, when you define it this way, is automatically the derivative of the integral is just 1 over x by the fundamental theorem of calculus, one of the two parts. Now you can do interesting things with this, like you can say, well, ln x is an increasing function because 1 over t is always positive, so you're always getting more and more area under the curve 1 over t as x gets bigger and bigger. That proves that ln of x is increasing, and all sorts of other things like that. So here's the idea. The natural logarithm is the area under the curve y equals 1 over t from 1 to x. And you can go backwards too and get minus the area. Well, now this leads to easy theorems, and you can see the proofs here. For any positive number, the natural log of a product a times c is ln a plus ln c. ln of 1 over c is minus ln of c. All these things that you're familiar with from algebra that I had to prove with great difficulty are easier. You can see the proofs here. I won't ask you to do those actually. Just by applying the formula we have that ln is defined to be the integral. Now, so you got all your usual logarithm properties. I won't go back and review those. Let's skip the numerical stuff too. And then you can show, because we know that the integral 1 over x was infinite, we proved that with L'Hopital's, well, not with L'Hopital's rule, but we proved that previously, that the limit is ln of x, as x approaches infinity, is infinity. And you can similarly do it backwards and go towards 0. So this integral thing, when you go back and look at your improper integral section, now you can prove these two results nicely. And then you can define e to the x to be the inverse of the function y equals ln of x. How do you know it has an inverse? Because you're integrating a positive function 1 over t, ln of x is an increasing function. An increasing function automatically has an inverse just by flipping it over the line y equals x, recall. And so the inverse function we call the exponential function. And then you can use that to show that the derivative of the exponential e to the x is just e to the x. Here's the proof. It said that the derivative ln of x is 1 over x is positive, so the derivative is always positive, it's increasing. And then the derivative of e to the x, by our formula that this is the derivative of the inverse of the logarithm, this becomes 1 over e to the x for the formula for the derivative of the inverse of a function. And then 1 over e to the x is just e to the x. You can prove easily the derivative of e to the x is e to the x with a short proof like that. And now e to the x gets defined for irrational exponents, ones that can't be written as fractions. You just define a to the x to be e to the x ln a, or I guess that says a to the r is e to the r ln a. But that allows you to define a power for an irrational number. If r can't be written as a fraction, you can still say what that value is, right? If this is a to the pi or something, or a to the square root 2. So all these things are reproved. The object in this section is not to reprove all these things, it's to be able to do a few different kinds of problems that come from these kinds of theorems. But you can prove these other results. Derivative of x to the r is r times x to the r minus 1. You can now prove it for irrational numbers, which wasn't so easy before. So it fills in all the holes for irrational numbers is the main thing this new definition does for you. All the mathematicians may find that interesting. We're looking at little details. The physics majors probably get bored, and the engineers and the chemists and all the other science majors, biologists. Here's an interesting result, though, that comes out of those. The limit as x goes to 0 of 1 plus x to the 1 over x actually is e. Right? Where e is the exponential function of 1. So, all right, so this is a theorem that limit as x goes to 0 of 1 plus x to the 1 over x is e. And similarly, by replacing x by 1 over x, you get, right, think of t equals 1 over x. Limit as t goes to infinity of 1 plus 1 over t to the t, just putting t as 1 over x in here, gives you limit of 1 plus 1 over x to the x equals e, which is kind of an interesting problem in the theory of interest, actually, just for fun. We'll do that one. If you have an interest problem where the amount of money that you have is your principal, the amount you invest, times 1 plus the interest rate r over n to the nt. This is the compound interest formula. If you have interest rate r annually and you compound r n times per year, then r over n is the money you get n times per year, and p times 1 plus r over n to the n is how much you get after a year, and if you take that t times, this is the compound interest formula. Well, if you now want to take the limit of this as t goes to infinity, as n goes to infinity, this becomes the amount, this is compounding an infinite number of times. What should you get if you compound infinite many times? If you get an infinite amount of money, what you get is the limit as n goes to infinity of all this stuff. The p can come out. And the formula we just had, suppose we put in r equals 1 for 100% interest. And suppose we do this for 1 year, so t is 1. So for 1 year, 100% interest, compounded continuously an infinite number of times, what do I get? Is n times 1. Limit 1 plus 1 over n to the n, we just said that's actually equal to e. So now let's also put in $1. So $1 at 100% interest for 1 year, you actually get $e at the end of the year. With infinite compounding, you don't get an infinite amount. More generally, the formula we just wrote, as n goes to infinity more generally, you get the amount is limit n goes to infinity 1 plus r over n to the nt for arbitrary interest rate and number of years t. This comes out by a similar formula. I would ask you to do that one. To be e to the p e to the rt. I forgot my p in here. PERT, the famous formula that you see in business. So this also allows you to derive the PERT formula. Just as a side comment, and a fun problem, not something I'll put on the test. Now we want to see the things that I will put on the test. But you can see that these are actually useful and very important theoretical results. Compounding infinitely many times per year doesn't give you infinite interest. For one, just get the P e to the RT formula for infinite compounding. If you define other logarithms, log base b of x be ln of x over ln b with a definition, then it defines logarithms to all other bases, also there are other formulas that are very important. When I worked in missiles in space, we had a missile would go off and get a gimbal angle, a thrust offset. It would thrust at a constant tilt. And it turned out the missile would go into a spin that was just this kind of integral, which is called a Fresnel integral, the sines and cosines here. And so these kind of integrals, these functions that look like this and are useful in applications can be defined as these integrals. This suggests that other integrals of use can be, or other functions of use can be defined as integrals also. So they'll point that out in this section. This is why we skipped this section. It's mostly theoretical results, but kind of interesting that useful things like the spin of a missile, spin up of a missile with a constant angle offset and constant thrust comes out to be defined as an integral. Let me look at the exercises based on this, and this is what I want you to be able to do. What is the integral from 1 to 1 over e of 1 over t dt? What should that be? So you want to be able to do a few tricky things like this. Well, you can do this out of the problems. The integral from 1 to 1 over e of 1 over t dt. The integral from 1 to x is ln x. So I just have to put x equals 1 over e. So this is ln of 1 over e. Remember that ln of m over n is ln of m minus ln of n. So it's ln of the logarithm of the quotient is difference of logarithms. ln 1 is equal to 0. You can prove that. That's easy to prove too, right? If you define ln of x be integral from 1 to x of 1 over t dt, then what's ln of 1 is the integral from 1 to 1 is 0. So ln of 1 is 0 is an easy proof also. And now ln of e is a similar proof. Comes out to be 1. So this is minus 1. So just as in algebra, this comes out to be 1. All right, so there's the first one. The answer is minus 1. Let's try some of the actual exercises down here now. So that says, sketch the curve y equals 1 over t and shade a region under the curve whose area is ln2. Well, remember that ln2 is defined to be the integral from 1 to 2 of 1 over t dt. Right, since ln x is integral from 1 to x. So this must be the area of the curve y equals 1 over t in the t versus y plane. And if you just go from 1 to 2, this area is actually natural logarithm of 2, according to the definition that we made. All right, how about number 4a there? Suppose I want to find the integral from 1 to square root a of 1 over t dt. What is that? Well, by this definition, this is ln of x if you go to x, so this must be ln of square root a. But you use your properties of logarithms, and ln of square root of a is a to the 1/2. And now you pull down the power and you get 1/2 ln a. And if ln of a is given to be equal to 9, this is 1/2 9 or 9/2. So that's how you can do these easy problems. wanted to point out this useful quantity. You probably saw this in algebra. Let's do it just because it's important. How can I write 9a, 3 to the x as a power of e? Right? Well, here's how you can do it, not like the algebraic way, but really they're saying do it out of the definition that a to the r was e to the r ln a, was that formula we wrote up there. I can write this as e to the ln of 3 to the x, and pull down the x and say this is e to the x ln 3. This is really the way they defined it in the book now. They said let 3 to the x be e to the x ln 3. I like to just remember it from the properties there. But there's the answer to that one. It's now a definition instead of a theorem. And now, how about we find some limits? One of the applications of this section that is useful is to be able to calculate limits like this. I wonder what, in 11a, the limit as x goes to infinity of 1 plus 1 over 2x to the x is. How could I evaluate that? This is not so easy, but we can think of it this way. This is, if I substitute u equal 2x, then x equals 1/2 u. And I could rewrite this as the limit, as x goes to infinity, u equals 2x also goes to infinity. So I'll write it as the limit u goes to infinity of 1 plus 1 over u to the 1/2 u. I'll write it u times 1/2. And now the u times 1/2 power is the, right, it is also expressible as one plus 1 over u to the u whole thing to the 1/2 power. And then you remember that when the limit of the inside thing exists, you can pull the power outside the limit and rewrite this as limit u goes to infinity, 1 plus 1 over u, oops, whole thing to the 1/2, take the power outside. And now limit as u goes to infinity, oops, forgot my u here. 1 plus 1 over u to the u is equal to e. So this is e to the 1/2. Or square root e. So a few limits like this you can evaluate by making this substitution that limit as u goes to infinity, 1 plus 1 over u to the u, this one, is equal to e. Or the other definition, limit of 1 plus x to the 1 over x as x goes to 0 from the right is e also, but we have both those definitions. Well, that's really all I wanted you to be able to do out of here. The rest of this I think is superfluous for us. Maybe we should just mention these right here on 25a. What if we want to take a derivative of a function that's defined as an integral? What is the derivative from x to pi, of the integral from x to pi of cosine of t cubed dt? This is really not particularly pertaining to this section. This is pertaining to the fundamental theorem of calculus section. But it's just reminding you of that since it happens to be doing functions defined by an integral. You say, hey, what if I have a function defined by this integral? What's its derivative? Well, what you're thinking is this. I could rewrite this as the derivative of minus the integral from pi to x of cosine of t cubed dt. And now, let's see, the derivative, the minus comes out, and the derivative of the integral from a to x is just this function plug in x. So the minus comes out, and then you get the derivative and integral undo each other, and you get cosine of x cubed instead of cosine of t cubed. So you can do the